European Union, also with the Research Council of Norway, and also my previous sponsor, Equinor. So today we're going to be traveling to the Arctic in the Barents Sea. You can see the location over there. And we're going to be looking at different seismic profiles and also well data and then core data, and also results from numerical modeling. So just to visualize what Grace mentioned, this is where I spent my bachelor and then moved north to Norway, in Bergen, and then up north to the Arctic, UIT. As you see, it's really close to the Barents Sea. This is the location, you can see it. And I also spent a bit of time at UNIS, University Center on Svalbard. Has anyone here been to Svalbard before or heard? No? It's a very exotic place. 2,000 polar bear living there, and you need to carry a rifle if you go to the field and do a sedimentary logs, because maybe it can pop up in the corner, but it's really interesting place. And yeah, this is a few pictures from my previous town in Norway. It's called Tromsø. It's within the Arctic Circle where I did my PhD. Oh,
if we can get rid of that sign.
Yeah. So thank you, Barents. So why do we interested in the high Arctic in the Barents Sea? This is a map I downloaded from Norwegian Offshore Directorate. So you can see that the green, they said I have to use this one. You see the green color, this is the Barents Sea, and this is the area open for petroleum exploration. So there's a high interest in energy exploration. And both academia and authority, we are actively exploring in terms of collecting data like 2D and 3D seismic, and also bathymetry, marine sediment cores, and so on. This is a picture of me in front of the seismic vessels owned by University of Tromsø, and this is on deck before we deploy our equipment to acquire seismic profile, and also related to the green energy like offshore winds, and also in the effort for net zero targets that we in the Barents Sea we also open for carbon storage. Yeah. So this is map showing you the oceanic gateway as a major conduit for ocean circulations. So you can see there are different areas that crucial or key for these oceanic circulations or thermohaline circulations, like the one in the Atlantic and Arctic, and also in Central American Seaway, here in the Tethys Seaway, and also from the Antarctic viewpoint. So you can see that it's back in time. So this oceanic gateway is strongly connected to or linked to the opening and closing of the continent, opening of the seafloor spreading and so on. But you can see there's a gap here. And what about the continental seaway? Like in the figure here, you can see that the red color and the blue is the ocean circulations along the slope in the Northeast Atlantic, but it's not very clear what happened in the Barents Shelf. So that's the area that we are investigating now in Bravo project. So you can see here, we try to understand when and how and the nature of the Barents Sea, Barents Seaway opened back in the Cenozoic time. So you can see that different paleotopography can have a different impact on your oceanic and climatic simulations. For instance, here in this first scenario, you can see that we have, if we imagine a closed Barents Seaway, and then the other one, if we have an open Barents Seaway, so you can give different model also for your simulations. And these two based on two different set of reference. So some people have reconstructions having this one model, and then the other one having this Barents Seaway open. So we try to understand a bit more further using seismic data, well data, and also the numerical modeling. So before I continue, maybe some of you not into sedimentology or not a sedimentologist, but here's an approach that I also taking into account in my study. It's called source-to-sink approach. So the idea is we try to understand the sedimentary processes and sedimentary system from source area all the way to the deep basin. We also try to understand their control and relationship between segment in the source-to-sink concept, like from catchment, shelf, slope, and basin floor. We also often try to quantify the dimension of the features like submarine fan here, and also the size of the channel, and also the canyon. And very often we try to predict what kind of catchment area back in time. So like this work by Tur Sommer, is also my collaborator. He's tried to link correlation between the what we found in the deep basin towards the catchment area. Like for instance, here, if you have a smaller submarine fan and how it look in the catchment. So it's usually linked with the typical small and large or in tectonically active system. And if you have a big or wide submarine fan, then you're gonna have a passive margin or mixed system. And we often use this kind of data like subsurface data, seismic and well, and also outcrop mapping, provenance analysis, and also numerical modeling. Yeah, before I continue, here is the plate reconstructions, just to give you an overview of the development. This one is during the late Cretaceous, or 75 million years ago. That's Greenland plate and Eurasian plate. You can see that that's the Greenland plate moved towards the Eurasian plate. And then during the breakup time, it's create even push towards the this side of the Eurasian plate and created the West Spitsbergen Fault and Thrust Belt on Svalbard. Meanwhile, in the south, we have the seafloor spreading. And during the Oligocene, we got a major change in plate reconstructions. So you see that Greenland now moved relatively northwards from the Eurasian plate, and we open up a big oceanic basin over here. And during the Miocene, around 17 million years ago, there's an opening of the Fram Strait because of the still Greenland moved towards the Eurasian plate and create a connection between the Northeast Atlantic and the Arctic. And then during Pleistocene, around 3 million years ago, we got a major glaciations. And this is also all the way from the Barents Shelf, Norway, and Europe too. And this is the present day situation of the Barents Shelf and Svalbard. You see there's a mid-oceanic ridge extending all the way from south to north and towards the Nansen Basin in the north. So in a few slides, I will talk a bit more into these three key time frame. Early Eocene, around 55 million years ago, and then Miocene, and Pleistocene. So during the breakup time, this is the plate reconstruction 55 million years ago. If we take a cross section over here, based on the field work, so you can see this mountain, Sturfula mountain up on Svalbard. So we can map this sediment linoform and sediment propagation from shelf all the way to the deep basin, and you can see the sedimentary logs and also photos from the turbidite system up on Svalbard. And in the offshore domain, that's from the onshore part here, and then here from the offshore part, we can also observe similar features. This is a seismic profile showing you a shelf edge clinoform, and also towards the deep basin, we can see this sandstone showing you the deep turbidite system. So if you're not familiar with this, sedimentology terms, so just try to remind you a little bit. This is a sedimentary system from delta to deep water setting. So if you have a fluvial system coming through and meet this ocean, and you have this delta system, and there's a sediment building up, prograding seaward, and it's called the delta clinoform, because clinoform can be different in sizes. So like this one, if you have only tens of meters water depth, and if you walk or swim along the way, crossing the shelf towards the slope, and here we have also this shelf clinoform building up, and this is the submarine fan in the deep basin floor. And then for the Miocene, so we have quite a bit of seismic data sets that we try to map this feature. So you can see that here, the green color is the Bjornøyer Fen drift or sediment contourite. So you can see the size is quite big. So this kind of feature we try to map and understand, because they are built or deposited because of the ocean circulations, ocean currents. A little bit more into introduction or background. So if you see this figure, you have this continental shelf edge and bottom currents often flowing parallel to the continental shelf, and created the sediment imbricated of the contourites. And the main or the key difference with the turbidites, you see here, the turbidite or gravity-driven current, it's mostly perpendicular from the continental shelf edge. And we can also see kind of similar imbricated and stack layers of sediments, but this is what we call levee, and this is the often we call channel levee system. So that's the difference between these contourites and turbidites. And in seismic profile, we can see also similar feature with this typically called contorted, with low to high amplitude seismic, and also kind of imbricated like that. And in the Northeast Atlantic, here we can see several features can be mapped along the Norwegian continental shelf to the north. And now I have also PhD students try to map on the northern part of the Barents Shelf. Yeah, and it's quite widely distributed too in the world. So you can see here, it's an example from Faroe Island. This is the mode, and this is the contourite drift, also in the lower part. And it's typically muddy deposits. Some can carry some fine sand too in core data. And in Pleistocene, this is the glacial or the Northern Hemisphere Glaciation. So you typically see these features of the sediment prograding wedge because of the ice sheet advancing towards the shelf edge, and creates this, we call it trough mouth fan. I will also come back to that. And this is the onset of Quaternary with the initial ice sheets in the northern part of the Barents Shelf. And then we have the last glacial maxima 30,000 years ago, and this is the present day situation of the Barents Shelf. And trough mouth fans. So this is a product of a glacial sedimentary process. So you can see if here there are two model. The first model, if we in the higher latitude, when the ice sheet eroded the shelf and created this debris lobes, and it's create a stack of debris lobes, or we call it glaciogenic debris. And then in the middle latitude, you see that it's more dominated by turbidites, and often it's channelized. And you can see that this is a model showing you the glacial erosion rate, and it's really powerful and erosive. Then it's created, it can deposit this huge fan or trough mouth fan. For instance, here in the southwest part of the Barents Sea, we call it Bjørnøya trough mouth fan. And this is an image seismic profile crossing the Bjørnøya trough mouth fan. So you can see that it can be really thick, up to 3 kilometers thick of glacial sediments. And we have several well data, so we have a good control of the age. And towards the deeper basin, so you can see it can be created these lances, features, or this glaciogenic debris. And for the middle latitude, you can see that it's more dominated by this turbidites, channelized turbidites feature. Here is a model of source to sink styles if you have a different slope and with glacial and non-glacial settings. So this is if you have a gentler slope, and above is non-glaciated and below is glaciated. So we can see that sediment clinoform and sediment block gradation building up. And if you have a strong currents, then you typically found this drift, sediment drift. And during the glaciations, you can see we have a thicker sediment glacial progressional wedge building up because of the ice sheet. So these two for the gentler slope. And what about if you are working on a steeper or steep slope? So we found out that that's not the case, that we can find a sediment progression, because you can see that they transform to debris flow, and also in the end created this turbidity currents. And also during the glaciations, if you are in the steep slope, then it's really tiny or a little progressional system if you have a depression or canyons like that. But mostly they evolve into debris flow and turbidites. So now we move on. What is the stratigraphic forward modeling, and why do we use it? So this is the method that I'm currently working on. So stratigraphic forward modeling is the use of mathematical equations or algorithm to simulate sediment erosions, sediment transport, and depositions. So why? What is the significance of this method? Is usually we want to test our hypothesis or geological concepts, especially if you are well, in the industry. Usually we come up with an idea, and we can also use this to test, and also to validate or evaluate our interpretations, like paleogeographical reconstructions. So if you are working with two different models of paleogeography, maybe you can also run this stratigraphic forward model to understand also the sediment source to sink. Yeah. There are several models available. I identify this that in academia is a model that we develop in UC called Wetlands and Gospel, and this is for more global model. And then in Germany, it's something called FastCage, and also in the US, LandLab. maybe some of you have been using that before. And also in the industry, something called GPM and dinosaur slow from Fram Lab in Paris. Now I'm going to show you what we've been using or working in Sydney. So this is called Badlands or Basin and Landscape Dynamics. So there are two or key concepts like climate and tectonics. So climate consists of precipitation and rainfall, and then tectonics usually about the uplift and subsidence, and also sediment transport and other aspects like sea level fluctuations and also longshore current. And here is just the, see if I can move it. So here's just the key concepts like mass conservation law. So elevation change is controlled by tectonics and erosions. And for sediment transport, we use stream power law. So you can see that erosion rate is a function of precipitation and also drainage area and slope. And for the source area, we use this downslope creep law. So elevation change is controlled by a topographic gradient. So with this kind of modeling, you can build your stratal stacking pattern of your geological data. And like this one, this clinoform, you can play around with the sea level and try to pick different sites. Then you can compare with your well data if you have a well control. And also, if you have a seismic profile, you can also compare with the seismic data. In terms of the source area, so you can also model what kind of catchment it looked like back in time. Like this one, it's different setting and measurement that you can input to your stratigraphic forward modeling. And this is open source code. It means that it's freely available. So you can just download and install to your laptop. And there are also few models available like Delta or RAVE or flexural model. Or if you are working with carbonate system, you can also use that. And this is just the interface of Badlands. So you can modify the codes. You can also add your own programs or coding and just run in your laptop. So now we move on to the case study. This is we applied in the Barents Sea. Here is the location of the study area in the southwestern part of the Barents Sea. And this is just the plate reconstructions in the Cenozoic time. So the idea that we want to test is about source to sink, or in this case, it's a multi-source to sink, because apparently if you are working in an active margin, active means that it's the plate moving and affecting the source area, then you can have a different sediment contributions to the sink, to your sink, like in this case, it's Greenland, and then or Staffanhei or Loppahei or mainland Norway in the southwestern part of the Barents Sea. And we use that software called Dinosaur Slow. So this is the study area. So you see here is the Loppahei, that's Staffanhei, this is the structural high, and this is this surface nugget basin. And here to the left is Lofoten Basin, it's just the magnetic anomaly. And we got a couple of seismic profile, 2D and also 3D, and also well controlled to calibrate our numerical modeling results. Here is an example of the representative seismic profile. So we are aiming at the early to middle Cenozoic. It means that below this thick glacial sediments. So we are looking at this section over here. And if we look at the well control, this is the chronostratigraphy, well to seismic type, and this is the tectonic events and the climatic events, and the input parameters for our model, the sediment load, and also eustasy, and precipitation and evaporation for the modeling. And one key important input for stratigraphic fault model is the initial bathymetry, because that's really creates major difference. And in order to do that, we try to make a backstripping analysis using this software called Move. So if you see the A panel, this is glacial sediments that we observe in the seismic profile, and you get Cenozoic pre-glacial sediments. So the idea is we removed the glacial sediments and then kind of put back on the shelf where it's supposed to, and then we restore the subsidence, and then it's going to be tilted, and it's created this paleobathymetry at 2.7 million years ago. And then we do that similar fashion until we get in the Eocene time. So in this case, if we remove that one, and we get the paleobathymetry at 23 million years ago. And now is the comparison of the modeling result and seismic data. This is the sand to map ratio, that's porosity, and that's thickness. And this is this isopach or thickness map from seismic profile. So we can compare later on, and also other studies investigating the system, the Eocene system. And you can see that it's largely similar. It means that we have a good modeling result. And I have one paper now in review. It's because now also incorporating seismic profile. So, and we have a data set from Equinor. They have a internal data or study. So we are able to map out this in well data, Apectodinium augustum. So it's a sign of the PETM event, and also Azola Acme, and this one is for the early Eocene climate optimum. But unfortunately, this Azola is very below seismic resolution, so we disregard that. So we only focus on the PETM. And from the 3D seismic data, this is a new data in the central part of the Sulphur Nugget Basin. So we are able to see this mid-ocean fans, and also what happened in the shelf area. And here in this profile, we are able to see that there's also channel levee system developed, supplying sediments towards the deeper basin, and created this submarine fans. So that was we call maybe like tectonic driven submarine fans here. But for the PETM fans, we try to map out with the seismic profile and see we found this northern PETM fans and also southern one. And again, with the source to sink in mind, we try to analyze where is the source area for that PETM fans. And we try to extract RMS amplitude maps for the pre-PETM, and then during the PETM window, and the post-PETM. And the pre-PETM, we see sign that it's not very strong, but during the PETM, it's very bright, this amplitude fans indicating the fans, and then the post-PETM, it's disappeared. So we thought that it's climatic driven submarine fans. And I'm also now involved in the ICDP proposals. It's called SPALCLIMB. The idea is try to map out or try to drill sediment cores in the western side of Svalbard here in the Forlandsundgraben, because we try to understand if we can see a sign of contourites, like I mentioned before. It's a sign for early ocean circulations. And we have submitted this project for abstract to IKMX or 10 next year in Bremen. So if you have time, you can also discuss this with us. And you can see some of the project participants. So the idea is to, you see, PETM and early Eocene Oligocene transition. Yeah, and back to the modeling. So this is the regional development from the numerical modeling results. So this is for the early Eocene, and that's the middle Eocene, and this location of study area. So we try to understand how the source look like when we have the modeling results like that one. And there's a study by group in the UK, and they try to analyze these 3 boreholes, one on Svalbard and then here in the southwest Barents Sea, using zircon analysis, and try to reconstruct the sediment routing system. And we can see that it's comparable between these 2 findings. So that's for the early Eocene and middle Eocene, and now this is also for Oligocene and Miocene. So the hypothesis is that we have a shelf-wide uplift during the Oligocene, and then also the Miocene with the regional exposure. But this is the million-dollar questions. So when did the Barents Seaway open during the Cenozoic era? And you can see that from our modeling, we don't have a good control of what happened in the source, because this code or this model, this software is only taking care of the basin part. So we move on, try to think maybe we need to change the algorithm. So now we change we move on to case study 2, source to sink in the Northern Barents Sea. And now we are using Badlands because Badlands also have a good control in the source and the catchment area and also to the sink. So now we are concentrating here in the northern part of the Barents Sea. That's Svalbard. You see Greenland over here. That's the central of our Arctic Ocean, Lomonosov Ridge. This is Nansen Basin. So we try to map out and model the landscape evolution. And this is the paleogeography from Tursomma. You see, this is for Paleogene. So you see there's a mounted building over here and there, and then shallow marine connections. But we don't really understand how it looked like. And we have a seismic control, luckily. Then we can compare later on our results of the model, like this K, L, M, and O from here. You see different lines. So we are looking at now the early to middle Cenozoic, which means this orange sediments that we will be using for calibration. Yeah. So if you still remember the source to sink concept, so we want to understand as well the source to sink approach here in the northern part of the Barents Sea. And for the sink area, you can see that this is the plate reconstructions back in 53 million years ago, with the separation between Lomonosov Ridge and the northern part of the Barents Sea. And also now in the Oligocene time, still moving northwards, the Lomonosov Ridge making a broader opening. And now this is the present day situations. So it's kind of straightforward. You see this the sink, and for the sink part. But then it comes the source area, and it's a bit more tricky because you can see this is different authors from different papers. You see here we have this kind of reconstruction and that one with one kind of coarse polygon. Here is even just create an area without any elevations. Here for widely used Scottish and right, even it's just shallow marine opened during 55 million years ago. So there's lots of uncertainties over here. So now we are concentrating, first part is the Eocene time, 55 to 33 million years ago. For the next step, we're gonna looking at more into Oligocene and also the Miocene. But first, try to understand during the opening of the Arctic or Nansen Basin. So I picked the Straume model, Paleodim at 55 million years ago. To your left is the Paleodim, the AM at 55. And this is the erosion deposition at 54. So I'll try to model the sediment transport and distribution toward the early opening of the Nansen Basin. So you see, this is Svalbard, this is Lomonosov Ridge, and Canada is over there. So you see this, the first filling is from the Eurasian Basin and very little sediment filling in the America Basin. And that's the drainage divide. Here, some parts of sediments deposited towards the Arctic Ocean and some parts towards the Barents Shelf. And I also tried to input or model or use the model of Scottish and Wright at 55 million years ago. And from the same angle, this is Greenland and Svalbard. That's Lomonosov Ridge. You can see also kind of similar early filling of the basin in the Nansen Basin, with major discharge from Greenland and Canadian Paleo Mountains, but little coming towards the Barents Shelf. From that model, you can also try to calibrate with the other studies, like this one is from Ingve Christophersen. Try to map out the Lomonosov Ridge. You see it's just lots of canyon system developed in the ridge, and kind of we have that also in the model. And here is the submarine fan feeding from the Canada side or from the Greenland part. And we can also observe the onlapping and downlapping patterns in the numerical model. If we take a cross section over here, so now we can try to compare what we see in the seismic profile. Like this one is from Geisler and Jokat. We observe this overlapping pattern and towards the early opening. So also here in our modeling result. Then back to this question. So when did the Barents Sea open during the Cenozoic era? For the early Cenozoic, from Eocene to Miocene, we don't have the answer yet. But in the Quaternary time, we have a new paper just out in RSES reviews. So you can see that the opening take place after 690 years, and this is the model. Try to simulate the landscape evolution from 2.7 to the present day. And during this time, the land bridge connecting the Svalbard and Novaya Zemlya collapsed and created this connection. So at least this is the first stage for the Barents Sea open, but this is for the Quaternary. In Bravo, we're still working, try to understand in the deeper time, back to the Eocene time, and also Oligocene and Miocene. And I have also a PhD student at UIT. His name is Orlando. It's part of a project called Dipole, led by Carmen and Jan Inge, also together with Grace. So we look at the Svalbard, northwest part of Svalbard with seismic profile. And here's a preliminary results. We have a horizon and then try to create this a two-way time surface and found this ridges and basins and yeah. And here is the seismic profile crossing these ridges. So you can see, maybe you cannot see, I need to press this first. So you can see now the basement interpretations running in black. So with this kind of study, we also we can get a clue what kind of sediments during the early basin filling went the opening on the northern part of Svalbard as for the input for our model. And here is another seismic profile. We try to link with the ODP wells in the north part of Svalbard. And here's the interpretation. So you see we have a quite good control in the shallower part, but it's getting unclear towards the deeper basin. Yeah. Yeah, this is just a summary. So we've been going through the stratigraphic fault modeling with Badlands and also looking at 2 case study in the north and in the Southwest Barents Sea and in the north. And yeah, I think that's all from me. I'm happy to take questions. Thank you.
Thanks very much, Amando. We have time for questions. We'll go right up the back to Will first and then come forward.
Thanks for the talk. Yeah, lots of stuff. I was just curious about the glacial plans. How long will those take to form? And then kind of a related question with your Badlands models. How long are the timestamps?
Well, this fan is it was created very short times, relatively short times during only glacial period in Quaternary or during the late Cenozoic from the last 2.7 million years ago. So it's really giving you an impression of really erosive agent of the ice sheet eroding the materials on the shelf towards the deep basin. As for Badlands, we are still developing for model the trough mount fan, but it's not done yet. It's still ongoing. We may adjust a little bit parameters, but it's not final yet, I think. Yeah.
Have you thought about essentially just looking at fossil record or when this gateway might open? I mean, things like both microfossils, but also macrofossils.
Yeah.
Is there any evidence to exchange species?
Yeah. For microfossils, yes, that's the thing. The Cenozoic sediment is very, very limited in the Barents Shelf. So we have a good control in the southwestern part of the Barents Sea over here, and a couple of the ODP wells. But in the central part or the eastern part of the Barents Sea, it was eroded because of the ice sheet. So that's why we try to incorporate the numerical modeling into the project too. Yeah, I agree with you with this biostrat data, and we use that a lot too in the southwest part. Yeah.
Yeah, just a similar sort of thing.
Yeah.
In this new target, you go into Western Svalbard, are you going to get marine sediments that you can somehow tease out whether the Arctic gateway was shut or?
The marine sediments.
Well, I don't know how these sediments work. Is it all just land-based sediments, or is there some?
You mean the shallow sediment core, like from marine cruise,
Yeah.
several meters. I guess for ICDP we are aiming for deeper drill, deeper core. We collect some data with the marine sediment cores along the Svalbard waters too here. But that's I guess back to the Holocene time, really shallow. But for ICDP, we're aiming for PETM, also for Oligocene, Eocene Oligocene transition, much more deeper, even deeper to Paleozoic. Yeah.
Have been discussions about.
Yeah.
And they're only going to be land-based.
Land-based, yes, land-based. IODP maybe not, because it's you know what happened with the
There's a lot of
situation.
pollutions
Mm,
with drilling this sheds.
Yeah.
Yeah.
yeah. Mhm.
So I have a question.
Yeah.
I know we'll talk about this more tomorrow, but it seems like the paleoDMs are a major control on the Badlands
Yeah.
results.
Mhm.
Have you tried sort of just a simplified case study of sort of basin high, basin low, as opposed to sort of all those fine features?
Yes, actually. Before I incorporated more into you know, like a continuous paleodim, try to test it out, just a simple model of the source losing profile, because we don't really understand the parameters like the climate or sediment delivery, how it looks. So before we incorporate that parameters, we test it in a simple paleodim.
Can you track sort of traces in Badlands? So like more provenance study based?
Yeah, that's what I heard from Tristan in Badlands, that there's an option where we can do it's called rock tracking, I think. So you kind of give an ID to specific rocks, and you will know where it might come from. So I think that's a good calibration too. Yeah.
I think that in combination with the paleoDM test will sort of help track if there's a preferential way of pathway.
Exactly. Exactly. Yeah.
Questions? If not, we'll wrap up. Thanks again, Armando, and instead of dinner this evening, we're actually going to go to lunch tomorrow. So everyone is very welcome to head over to Canberra. We'll leave at about 12:15 in the gap between J2 and J8. So bring your lunch or buy lunch in Canberra, but hope to see you tomorrow. Thank you very much. It's Monday.
Hi, can we have a copy of the,
Yes.
hello, can you hear me? Can we have a Hello? Hindi talaga siya gumagana yung ano mo siya, yung mic mo.
Kita mo kahapon.